Welcome to your nuclear chemistry podcast. First, to start off, just a bit of review for the notation that you're going to see. We know that our nucleus of an atom contains protons and neutrons. We know that isotopes are different versions of that element. And in order to be an isotope, the atomic number can't change, because changing the protons would give you a new element. But the number of neutrons can change. And changing the neutrons is what's going to give you different masses. A term you haven't seen before, though, is the term nuclide. Since in nuclear chemistry, we're not worried about what the electrons are doing, it's just the nucleus of that atom. The atom itself gets referred to as a nuclide, as in we're only caring about the nucleus. You're going to see these symbols written one of two ways to identify one isotope from another. Sometimes you'll see just the element and the mass number. Sometimes you'll see a little bit more information, that element and mass number plus the atomic number. If both numbers are listed, the mass will always be on top and the atomic number always on the bottom. But if we take a closer look at this nucleus, the things that we find in our nucleus, as we know, are protons and neutrons, and that's it. There is a generalized term to mean either of these things. The term nucleon just means thing in the nucleus, so general word for proton or neutron. Now, because that atom is made of protons, neutrons, and electrons, you would expect that the mass of an atom would be the sum of the masses of all the things present. But if we add up the exact masses, that's actually not what happens. So for example, if I look at a helium atom has 2 protons, 2 neutrons, and 2 electrons. And if I take the exact mass of each individual subatomic particle and add them all together, I end up not getting exactly the same amount as the measured mass of one whole helium atom put together. This missing mass here is called a mass defect. And there is a measurable difference in the mass of the whole atom as opposed to the sum of its parts. So where does that mass go? Okay, so like I said, the difference is called a mass defect. And that mass defect, along with probably the most famous equation in all of science, actually explains how the nucleus of the atom is held together. That mass actually gets converted into energy. So even though you have a very, very small change in mass, that mass defect was a tiny amount of mass, it gets converted into a very large amount of energy. That energy is called nuclear binding energy, or the strong nuclear force. And it's what actually glues the protons and neutrons together. It's the reason a nucleus can stay together, because protons all have positive charges to them. So I shouldn't be able to keep a whole bunch of positively charged things all next to each other. The electrostatic repulsion should push them all apart. But it's the energy that comes from this very slight conversion of matter to energy that binds the whole thing together. This graph you saw on your activity from the other day, a graph of stable isotopes. What makes something stable or not depends on the ratio of protons to neutrons in that nucleus. This band of stability that you're seeing here shows all the different ratios of protons to neutrons that are stable. If you're outside of this band of stability, then you're going to get something that's radioactive or unstable. For the smaller atoms, way down here at the bottom, a 1-to-1 ratio is the most stable, a neutron for every proton. However, the larger that atom gets, the more neutrons you have to hold it together. Remember, large atoms will have lots and lots of protons, lots of positive charges all right next to each other. You have very, very strong repulsion between those protons. So you need more and more neutrons in there gluing it together. If you have something that is unstable, it's going to undergo radioactive decay. This is what transforms unstable isotopes into stable isotopes of other elements by giving off or transforming particles. The rate of change for this is called a half-life. That half-life tells you the amount of time required for half the sample to decay. And they are all exponential decay curves like this. The length of time represented by each half-life, that can change. So this x-axis down here could represent different amounts of time. This could be 5 seconds, 5 seconds, 5 seconds, 5 seconds. But the general shape of that curve should be the same every time. So if we take this idea of a half-life being the amount of time it takes for half your sample to decay, you should be able to figure out some different amounts in here. So take a moment, see if you can figure these out, and then we'll walk them through. For number one, The half-life is 3.824 days. After what length of time would a quarter of the sample remain? The key is to know how many half-lives have occurred. And the good news is you will only deal in a whole number of half-lives at a time. I am not going to make you do the actual exponential decay equation to calculate any point along that curve. We're going to deal with whole numbers of half-lives. So if I have one half-life go by, half my sample should decay. If I have two half-lives go by, a quarter of my sample should decay. So this is or a quarter of my sample would be left. So what this tells me is 2 half-lives worth of time have gone by. If one half-life is this long, times 2, means this is the length of time that it would take for a quarter of the sample to decay. 2 half-lives worth of time. For the second question, again, I'm given the length of time for a half-life. How many milligrams of this would be left after 57.2 days if I start with 4 milligrams? So the key is to figure out how many half-lives is that. So you'd have to divide 57.2 by 14.3. That tells you how many half-lives have occurred. And then you just cut your sample in half that many times. Now, all radioactive decay is not the same. There's different types of particles that can be ejected from the nucleus, different processes that could happen. And you modeled a lot of these processes in that POCL activity that you did. So the first type of radioactive decay is an alpha decay. Alpha decay means you've got a particle with 2 protons and 2 neutrons being kicked out of the nucleus. So it's essentially a helium nucleus, no electrons involved. So here's an example of what an equation could look like. If I start off with polonium-210 and I kick out a particle that has 2 protons, total mass of 4, so 2 protons, 2 neutrons, then what's left is going to be whatever makes the math work. In other words, I started off with a mass of 210, I kicked out 4 particles, therefore I've got a mass of 206 left. I started with 84 protons, I kicked 2 of them out, therefore I have 82 protons left. And the atomic number tells you what element you have. As far as radiation goes, it's a very large particle, so alpha particles are pretty easily shielded. Not a lot of energy there. So now take a moment to see if you can write a nuclear equation to figure out, if I start off with radium-226, what am I going to end up with? So if I take my radium-226, I have to look up that its atomic number was 88. My alpha particle is this thing right here, so I know that has to come off. Then it's just a matter of doing the math. 226 minus 4 would give me 222. 88 minus 2 would give me 86. And then I just need to look up the atomic number to tell me what element that's going to be. Looks like I forgot to look at I don't have my periodic table right in front of me, so we'll just have to look up whatever element that would be. For my second one here, if thorium-230 undergoes an alpha decay, what will my product be? Oops, same process here. 230 minus 4 gives me a mass of 226. 90 minus 2 would give me an atomic number of 88. Then I would have to look up atomic number 88 to know that it was radium. For beta decay, beta particles can be actually a couple of different things. This is a category of radioactive decay. You could have electrons or positrons. Positron being the antimatter version of an electron. They're much smaller than alpha particles, so they can penetrate through matter a little bit further, although still relatively easily blocked. Beta emission, in general, is going to give you an element with the same number of nucleons, meaning the mass does not change. No change for the mass. But it is going to change the ratio of protons to neutrons, which means you're actually converting protons to neutrons or the other way around. This beta decay can happen 3 different ways. By far the most common is beta emission, so giving off a beta particle. That means that a neutron gets converted into a proton and an electron. Then the electron gets kicked out because electrons do not belong in the nucleus. So the result is that the mass stays the same, but the atomic number actually increases because a neutron got converted into a proton. So now there's more protons in the nucleus than there were before, but less neutrons. So here's an example of what that equation could look like. Carbon-14, when it decays, undergoes a beta decay, gives off that beta particle. You'll see it written like this, or with an E for electron, means the same thing, mass of 0, but charge of -1. Then to figure out this particle, I have to do what makes the math work. I've got -1 plus something has to equal this 6. Okay, my atomic number went up by 1, but the mass doesn't change. Electron capture is exactly the reverse. One of the inner shell electrons can get sucked into the nucleus, and if it gets pulled into the nucleus, it will combine with a proton and form a neutron as a result. So now notice that I've got my beta particle here on the reactant side, on the left side of the arrow. It joins into this silver atom, causing your atomic number to go down by 1 because there's one less proton, but the mass to not change because that proton turned into a neutron. Positron emission means now a proton is the one changing. It gets converted into a neutron and a positron, and then the positron gets kicked out. Positron is a positive version of an electron. It's actually an antimatter version. So still no mass, but with a +1 charge. Notice my mass number does not change, but my atomic number goes down by 1 because a proton got converted into something else. All right, take a moment, pause the podcast, see if you can predict how to write an equation. Carbon-11 produces a positron. Here's my positron particle right here. Mass of 0, charge of +1. Then you got to predict what would make the math work. Mass number doesn't change. Atomic number would have to go down by 1, so that way the total atomic number on left and right still match. Then you would look up atomic number 5 to know that it's boron. For bismuth-214 producing a beta particle is a normal electron. Oops. There we go. Beta particle being a normal electron here. So my atomic number goes up by 1 because I have an increase in protons. But my mass number did not change because that proton came from a neutron being converted. And then the last one for neptunium producing an alpha particle. Alpha particle here has a mass of 4, atomic number 2. So these are the resulting numbers I get. My atomic number went down by 2, mass went down by 4, and looking up atomic number 91 is what tells me my element. Let's try it in reverse. If I give you the equation, can you work backwards to what's the missing particle and therefore what type of decay? Pause the podcast, give that one a shot. For the first one, the only thing that would make the math work here is for this to be an electron. 79 minus 1 would give me 78, but 195 plus 0 would give me 195. So with this charge and atomic number, that's what tells me that has to be a beta particle, and therefore electron capture, because it's on the left side of the arrow. Over here, the only way to make that math work would be for this to be a +1, because 19 equals 1 plus 18. Mass number, though, has to be 0, so it's 38 on both sides. That would make this a positron, and therefore positron production, or positron emission. Gamma emission, or gamma rays, these are not particles. This is that highest end of the electromagnetic spectrum, high energy photons, and just occurs with other types of decay. So here you see an alpha decay and gamma rays coming along with it. Not something you'd have to predict, just want you to see that this is our highest energy form of emission. If you were to rank these types of radiation in order of increasing energy or ability to penetrate matter, alpha the lowest, beta next, gamma much, much higher penetration. Last thing we've got are nuclear reactions. Got two different categories. Fission, where a nucleus splits into smaller nuclei, just kind of breaks apart. You get a lot of energy because the mass of the products is less than the mass of the reactants. That mass gets converted to energy, just like with our nuclear binding energy. With fission, spontaneously very slow, but you can induce it to be much faster if you throw a whole bunch of neutrons in there, causing each one in succession to continue to divide. With fusion, here you've got the opposite process, smaller atoms combining to produce much, much larger ones. This is what you see in the